Hey folks, my name is Nathan Johnston. Welcome to lecture 14 of vector calculus. In today's class, we're going to introduce something called a vector line integral, okay? And we're going to talk about, what it is, what it represents, how to think about it, and we're going to get as far as developing a formula that lets us actually compute it in practice, okay? And then next lecture video, we're going to do a bunch of examples, compute things with it, and talk about physical interpretations and that sort of stuff. But for now, just what the heck is it? What's a vector line integral, okay? And as the name suggests, it's a line integral, very similar to scalar line integrals from last week. The difference is instead of taking place over a scalar field, it takes place over a vector field. Okay, so remember, what was a scalar line integral? Okay, it was you had a scalar field in the background, and then you had a curve going through it, and you imagined accumulating values of the scalar field as you walked along the curve. A vector line integral is very, very similar, except instead of having a scalar field in the background, you've got a vector field in the background. And the thing that you accumulate, it's not quite values of the vector field. Instead, like we want to accumulate some sort of scalar quantity so that we get a number at the end of the day. So what we're going to accumulate as we move along the curve is we're going to accumulate something that sort of tells us how much the vector field and the path or the curve are pointing in the same direction. Okay, so in this picture here, if we've got a curve, so we're going from the top left to the bottom right, so I've parameterized it by some path, okay, then what I do is at each point along this curve, I ask the question, okay, is the path and the vector field, are they pointing in the same direction or the opposite direction or perpendicular to each other or what? And I ask sort of like, how much are they pointing in the same direction? A little bit more formally, what is the component of the vector field that's pointing in the direction of the path? Okay, so let's talk a little bit about like what a component is and what it means, okay? But it's our way of measuring this overlap, how much two things are pointing in the same direction. Okay, and if you've taken linear algebra, you know what a component is already. I mean, component or coordinate in exactly the same linear algebraic sense that you might have seen earlier, but let's talk about it so we're all on the same page, okay? So first off, if I just talked about like an x component or a y component, you could probably guess what that means. If I've got some vector and I say, yeah, what's its x component? You would just say, oh, well, it's the first entry in that vector. It's how far it points in the x direction, okay? In other words, like if I was to draw a right angle triangle where the hypotenuse is my vector in question and one of the legs is, on the x-axis, then the x component of that vector, it's just, well, how long is that leg of the right angle triangle? Okay. And then if I said, well, what's the y component? I would just do the same thing with the y-axis, right? Like right angle triangle, hypotenuse is the vector in question, and then the y-axis is where one of the sides of the triangle lies. The length of that leg of the right angle triangle, that's the y component. Okay, there's nothing actually special about x's and y's here though, okay? I could ask about components in other directions. So if I have the exact same vector, okay, but now I say, okay, what's its component in this direction? You do the exact same thing. You just draw a right angle triangle, and what I mean by component is, well, how long is this leg of the right angle triangle? In other words, like this vector here, how much of it is pointing in this direction? And then there's this little leftover piece pointing in some other direction, okay? But how long is this piece in the direction that we're talking about? That's what a component is. All right, fine and dandy. How would we compute it though? How do we compute components? And okay, we're just going to do a little bit of mild trig and turn this into some linear algebra stuff. Okay, so what I'm going to do is I'm going to say, okay, I want to do some linear algebra stuff to compute this. I'm going to give a name to a unit vector that's in this direction that, I'm trying to compute a component in that direction. Okay, so I'm going to call the unit vector in that direction, I'm going to call it u. So the vector of length 1 in that direction is called u. And I'm going to say that theta is the angle between these two lines here, okay, between the vector and the line. Okay, so in other words, between this vector, which I'm going to call v, and that unit vector that I just introduced, that angle there is theta. Okay, so just redrawing my picture down here, now it looks like this with a u thrown on and a theta thrown on. Okay, and I mean, if you just do some mild trig, if the length of this vector is length of v, then the length of this side of the right angle triangle must be length of v times cos theta, right? That's just sort of introductory trig stuff. The other side, if I wanted to find its length, it would just be length of v times sine theta. But no, I want the adjacent side, so it's length of e times cos theta. Okay, and that's fine and dandy. Okay, I don't want to use that formula though. I hate trig. I like avoiding trig whenever I can, especially if in the next step I'm going to be integrating over this thing. Okay, so let's do some linear algebra magic. We remember from linear algebra The cosine of the angle between two vectors, well, that can be expressed in terms of dot products and vector lengths, right? The cosine of the angle between u and b, that's their dot product divided by the product of their lengths. Okay, so I'm making that substitution there, and then something really magical happens. There's a length of v down here, length of v up there, those cancel out. Length of u down here, well, I specifically chose u to be a unit vector to have length 1, so that's just equal to 1. It goes away as well, and you're just left with the dot product between u and v. So that's how I measure how much vectors are overlapping. Okay, I leave one of them alone, I scale the other one so it's a unit vector, and then I just dot product. That gives me the components of one of them in the direction of the other one. Okay, so with that in mind, how should I compute vector line integrals, right? Like, what should my formula for a vector line integral be? Well, I should just integrate from one endpoint of the curve to the other. And what should I integrate? Well, I should integrate a dot product that tells me how much the path is overlapping with the vector field. And that's exactly what I'm going to do. Okay, so suppose you've got some domain in n-dimensional space, you've got a vector field acting on that domain, and you've got some curve living inside the domain so that the vector field is defined on it. Okay, well, what we're going to do is we're going to parameterize that curve by arc length. I'll talk about why in just a second, but parameterize it by arc length, which we know we can always do. Then the vector line integral, it's defined to be this quantity here. Okay, so this is a bit of a mouthful. On the left here, let's talk about the left first. So first off, the left-hand side, that's just notation, okay? When we write integral over a curve, f dot dl, that's just notation that tells you, oh, this is a vector line integral. And it's very similar to our scalar line integral notation. The only difference was here you had a scalar field, little f, and here you didn't have dot dl, you had just a dl, like a scalar quantity dl, where here, like, it's a vector quantity that's being dotted with it. Okay, and this notation is just meant to be sort of suggestive of this fact up here, that what we're doing in a vector line integral is we're accumulating dot products. We're accumulating how much two vectors overlap, the vector field vector, and this thing, which is sort of like an infinitesimal vector in the direction of the path. That's what this notation is sort of getting at. All right, but how do you actually compute it? Like, what's the formula for computing this? And that's what's going on the right-hand side here, okay? So how you compute it is, well, here's the vector field at a particular point on the curve. And here, this t of l, that's the unit tangent vector at that same point on the curve, okay? This t of l, that's the velocity vector divided by the speed. We talked about this a few lectures ago. This is the unit tangent vector at that point on the curve, okay? So this t of l, this is playing the role of u in our dot product from earlier, okay? It's a unit vector in one of the directions. This is a non-unit vector in the other direction, so that's playing the role of v, and when I dot them together, I get how much they're pointing in the same direction, okay? And then I accumulate that quantity, I integrate it over the entire curve. Okay, so that's all this formula is. If you're wondering why on earth do we have to use a parameterization by arc length, it's for the same reason that we had to do that for scalar line integrals, right? I don't want to be accumulating things relative to how much time has passed for a particle tracing out the curve. I want to accumulate things relative to how far I've moved along the curve. I want this to be a path independent quantity. I want it to just depend on the curve itself. So that's why I define it in terms of a parameterization by arc length. Okay. So, great. We have a formula for it, just a definitional formula, but it's a formula. In practice, it sucks, right? In practice, we can't make use of that formula because for most curves out there, I don't know how to find a parameterization by arc length, okay? That was that hideous thing where we've got, compute an ugly integral, then invert a function, things that we can't do in practice, okay? So, I would like a formula that I can actually do computations with. In other words, I would like a formula that does not rely on a parameterization by arc length, but just relies on any parameterization, whatever parameterization I can find. Okay, and fortunately, yeah, we can do this. We can come up with a formula that works for any parameterization, any path. So what we're going to do is we're going to say, okay, well, if x tilde is a parameterization by arc length, I can think of that as coming from some other path, some other parameterization that's not necessarily by arc length, okay? This is stuff that we did back in lecture video 5. Okay, so if I have any path, I can turn it into a parameterization by arc length via this. I figure out how time and length along the curve relate to each other, and I do this sort of substitution. And if I take this and I plug it into my definitional formula for the vector line integral, then what happens? Okay, well, what I'm going to get is, well, notation for vector line integral equals, well, here's the definitional formula for vector line integral. And then what I'm going to do is I'm going to say, okay, x tilde, no, that's x of t of l now. Okay, so x tilde of L becomes x of t of L. Okay, I've sort of suppressed the L here because what I want to do is I want to think of this as an integral with respect to t now. Okay, so x tilde of L becomes x of t. And then the unit tangent vector of L, okay, I'm not really changing that, but again, I'm just sort of switching my perspective here. I'm going to write that as t of L of t because, again, I want to think of this as a function of t. Okay, so I didn't actually change anything, with t of L to t of L of t, just change how I thought about it. Okay, and then I'm going to do a change of variables in the integral. Okay, I'm going to say, no, I don't want to integrate with respect to little l anymore. I want to integrate with respect to t. And the way you do that is you have to introduce a dl by dt in here, right? This is change of variables for integrals. It's something that you saw back in calculus 2. Okay, so, and like the way that you think about this is, oh, the dt's cancel and I just get back to dl like I had over here. Really, it's chain rule going on, but that's sort of the idea. Okay, and you have to update your endpoints of integration as well. This used to be little l goes from 0 to big L. Now it's t goes from t of 0 to t of big L. Okay, fine. This is not too bad of a formula, okay? But I mean, you can simplify it and clean it up a little bit better by noticing that this thing over here, this is the unit tangent vector at a point times the speed at that point. And if you multiply them together, what you get is just the velocity at that same point, okay, right? Because how did we define the unit tangent vector? Well, it's just velocity divided by speed, which is what dl by dt is. Okay, so this whole thing over here, that's just the velocity vector. And then when you put this all together, here's sort of a version of the definition that we saw a moment ago, but turned into an actual computationally useful thing that doesn't rely on parameterization by arc length. It just works with any path. Okay, so again, suppose you've got some domain in Rn, you've got a vector field acting on that domain. You've got a curve inside that domain so that the vector field is defined on it. Okay, now, we don't need a parameterization by arc length. We just need any C1 path. We need any path that has continuous first derivatives. Then the vector line integral on that curve in that vector field is, well, same notation as before. We're not changing the notation. But how do we compute it now? Well, just integrate along the path. So t is going from A to B. And vector field at the point dot producted with the velocity vector. That's exactly what we proved up above here. Okay, and that's our formula for actually computing it in practice. And this is nice because, usually it's a lot easier to find just some parameterization rather than a parameterization by arc length. All right, fine and dandy. Let's do one computational example here and then wrap up. Okay, so let's practice using this formula here. Let's evaluate the vector line integral over some curve. Here's my vector field, this y minus x comma xy. That's my vector field. That's my f. And dotted with dl. Okay, so like here, I didn't specifically say vector line integral. I just said line integral. Okay, and you can figure out from which notation is used, which type of line integral you've got to compute. Here, I've got a dot product in here. I've got a bold L there. Oh, this, I've got a vector field here. This is a vector line integral. Okay, it's not a scalar line integral that we did last week. All right, so how do I compute it though? Well, I just need to compute all the bits and pieces up in this formula up here. Okay, so my vector line integral by that theorem directly up above equals this. This is my formula for it. I need the velocity vector. Okay, so let's compute that. Take the derivative of each entry. T squared becomes 2t. T cubed becomes 3t squared. So I'm going to replace this x prime of t by that velocity vector. And then over here, f of x of t. Okay, well, that means that, the first entry of this vector, f of x of t, is y minus x. Y is t cubed, x is t squared, right? I'm getting these y's and x's from my path. Okay, so I'm going to get t cubed minus t squared in that first entry of my vector field. Okay, and then my second entry is x times y. In other words, t squared times t cubed. Oh, that's t to the power 5. Okay, and now it only depends on t, so I'm going to be able to compute this, right? I'm going to be able to compute, it's an integral of a one variable function, right? If I do this dot product, I get t cubed minus t squared times 2t, that gives me these first two terms here, and then plus t to the power 5 times 3t squared is 3t to the power 7. That's a function of one variable. I integrate it from -1 to 1. I know how to do that. That's a problem from an earlier calculus course, right? So, every one, like it's just a polynomial. Every one of these exponents just increases by 1 and you divide by the new exponent. And at the end of the day, you just get a value of 4/5 for that integral. So that's what the vector line integral is. Okay, and sort of one thing that this tells me, okay, so you can sort of see the curve and the vector field here. One thing that this tells me As the particle moves through the vector field along that curve there, the vector field, it's pointing with the particle more than it's pointing away from it, right? Like sort of the overall contribution is positive here. So that it's sort of overall the particle is moving with the direction of the vector field rather than away from it. There are some spots where it's moving away from it or contrary to it, but overall the net contribution is positive. All right, so that's all we're going to do today. Thanks for watching, everyone. Next class, we'll do a whole bunch more examples. We'll talk about how to think about this physically. All right, so see you then for that.